In July of 1832, a landslide exposed a cluster of enormous fossil bones on the bank of the Ouachita River, in what was then a fairly remote stretch of Louisiana. A local landowner, Judge H. Bry, wrote to the American Philosophical Society describing the find, and buried in that letter is a detail that tends to get people's attention. Some of the bones had already been found and put to use by a local resident as andirons, the metal bars you rest firewood on inside a fireplace. Somewhere in Louisiana in the early 1830s, someone was burning logs over the ribs of a prehistoric whale without having the faintest idea what it actually was. When the surviving bones eventually reached the naturalist Richard Harlan in Philadelphia, he didn't know what it was either. Not really. And the guess he made, publicly, in print, turned out to be so wrong that scientists have spent nearly 2 centuries stuck with the wrong name anyway, because of a technicality nobody's been able to undo. Harlan presented his findings to the American Philosophical Society in October of 1832 and published the full description 2 years later, in 1834, under the fairly dry title Notice of Fossil Bones, found in the Tertiary Formation of the state of Louisiana. What he had to work with was several fragmentary vertebrae, plus one single vertebra that had survived nearly intact, genuinely massive in size. Harlan compared it against everything he could think of: Mosasaurus, Geosaurus, Megalosaurus, Iguanodon, Ichthyosaurus, Plesiosaurus. He concluded the closest match was Plesiosaurus, the long-necked marine reptile, and classified his new animal within the same broad reptilian grouping. Working from the size of that one vertebra, he estimated the complete animal at somewhere between 80 and 100 feet long, guessed the full skeleton would weigh over 2 tons, and proposed, almost tentatively, that if future discoveries confirmed his reptilian red on the material, the genus ought to take the name Basilosaurus, king lizard from the Greek basileus and sauros. Separately, that same year, additional material reached Harlan from Alabama, sent by a judge named John Crea in Clark County, adding to what was becoming a genuinely significant fossil haul, all of it still filed, in Harlan's mind, under giant sea reptile. Here's a small nomenclature detail worth knowing, because it changes how you should actually read the animal's full scientific name today. Harlan's 1834 paper only ever names the genus Basilosaurus. It doesn't attach a species name to it. That part came later from an entirely different source and under circumstances that turn out to be a little ironic. In 1839, Harlan personally carried a selection of teeth, jaw fragments, and additional bones across the Atlantic to England, and showed them to a rising figure in comparative anatomy named Richard Owen, the same Richard Owen who, around this same period, was doing the foundational work that would soon lead him to coin the word Dinosauria entirely. Owen examined the material and noticed something Harlan's original description had missed. The molar teeth were double-rooted, a dental structure that simply doesn't occur in fish or in reptiles. It's a mammalian feature, and once Owen looked at the rest of the material with that in mind, he concluded the animal wasn't a giant sea lizard at all. It was a mammal, specifically something allied with whales. For a brief stretch, by the way, even Owen's own read wasn't fully settled, since some of his early thinking floated the possibility the animal might have been a plant eater, comparable to a manatee or a dugong, before the genuinely predatory shape of its teeth became better understood. Owen ultimately proposed scrapping Harlan's name entirely in favor of something more accurate, Zeuglodon, meaning yoke-tooth, describing the distinctive shape of the molars, and published the species as Zeuglodon cetoides, whale-like yoke-tooth. Harlan, to his credit, reportedly agreed this was the better, more honest name for what the animal actually was. And it didn't matter. Under the rules that govern how scientific names get assigned, called the principle of priority, whichever validly published name comes first wins. Permanently, regardless of how much better a later name might describe the animal, and regardless of whether the original name is actively misleading. Harlan published Basilosaurus in 1834. Owen published Zeuglodon in 1839. Basilosaurus was 5 years earlier, so Basilosaurus is the name that stuck, king lizard, officially, on the books, for an animal that both of the scientists involved in describing it agreed, within a decade of its discovery, was not a lizard, not a reptile, not anything close. Zeuglodon became what's called a junior synonym, a name that survives only informally now. in old literature, on some state fossil listings that print both names side by side, and in the regional nickname some parts of Alabama still use for the fossil-rich country where these bones kept turning up. Basilosaurus cetoides, formerly credited today as Owen, 1839, for the species portion, even though Owen was trying to get rid of the genus name entirely when he coined it. The wrong name simply arrived first, and nearly 200 years of scientific consensus that it's wrong hasn't been enough to change it. It got stranger before it settled down, too. The fossil's growing popularity through the mid-1800s led to one of the more colorful frauds in early American paleontology, a traveling exhibit called the Hydrapion, or Hydrarchus, depending on the source, a composite skeleton assembled from the bones of multiple different individual whales, stitched together and marketed to paying audiences as a genuine sea serpent. It's a good reminder that the original reptile misidentification wasn't some isolated academic slip. The animal's bones were genuinely, viscerally serpent-like enough that people kept independently arriving at the same wrong conclusion. Reputable naturalists and traveling showmen alike. For years after the mistake had technically already been corrected. So, what was Basilosaurus actually? Fossils place it in the late Eocene, roughly 41 to 34 million years ago, with major deposits along the American Gulf Coast, particularly Louisiana, and a cluster of counties in southern Alabama, where the fossils turned up in such abundance that Basilosaurus cetoides is now the official state fossil of both Alabama and Mississippi. The single richest and most scientifically important site for this animal and its close relatives, though, is Wadi Al-Hitan, the Valley of the Whales in Egypt's western desert, a site so significant it was designated a UNESCO World Heritage Site in 2005, specifically for containing hundreds of exceptionally preserved early whale fossils, unmatched anywhere else on Earth, for demonstrating exactly how whales made the transition from land to sea. And that transition is written directly into this animal's body. Basilosaurus was long, genuinely long, estimates generally running between 15 and 20 meters depending on the species, but it didn't look anything like a modern whale stretched out. Modern whales have a compact, torpedo-shaped body built for efficient swimming. Basilosaurus had an extremely elongated, serpentine build instead, driven by individual vertebrae that were roughly 3 times longer, relative to their width, than in other, more conventionally built basilosaurids, strung together across a spine with somewhere around 66 total vertebrae in a well-documented Egyptian specimen. It had no forehead melon, the fatty structure modern toothed whales used to focus echolocation clicks, and a long, robust skull packed with conical, serrated teeth built for actively seizing and tearing prey. Not the specialized suction-feeding or precision echolocating hunting styles you'd see in living whales today. Then there's the detail that made this animal genuinely important to the broader story of whale evolution, not just a curiosity. In 1990, a team led by paleontologist Philip Gingerich described the first functional pelvic limb and foot bones ever recovered from any cetacean, fossil or modern, pulled from a Basilosaurus isis skeleton in Egypt. Small back legs, a pelvis, a femur, a tibia and fibula, and tiny, fully formed foot and toe bones, sitting on an animal that, by every other measure, was already a fully aquatic, ocean-dwelling whale. These legs were far too small to support the animal's weight or contribute meaningfully to swimming. They were, functionally, useless for locomotion. But here's what makes them more than just a leftover. The muscle attachment sites on these bones are well developed, not the kind of anatomy you'd expect from a structure that had simply stopped doing anything at all. The leading functional hypothesis, based on that muscle anatomy, along with apparent size differences between individuals, is that these tiny hind limbs were being used as claspers, positioning aids that help stabilize mating in an animal with an extremely long, flexible, serpentine body. Not unlike the small vestigial pelvic spurs, some snakes, like boa constrictors, still used for exactly the same purpose today. It's a genuinely well-supported explanation, built on real comparative anatomy. Though it's worth being upfront that it remains an inference about behavior nobody could ever directly observe, rather than something proven outright. What was it actually hunting? Here, the fossil record gets about as direct as paleontology gets. At Wadi Al-Hitan, researchers have recovered Basilosaurus isis specimens with the remains of juvenile Dorudon atrox, a smaller, related early whale, along with large fish, preserved directly inside the ribcage region. Genuine stomach contents, not just circumstantial association. Separate studies of juvenile Dorudon skulls found bite marks matching adult Basilosaurus dentition, precisely in size and spacing, concentrated specifically around the skull, consistent with a predator targeting the head for a killing bite, likely by raiding Dorudon nursery or calving areas and preying specifically on calves. A number of predated Dorudon skeletons turn up disarticulated, scattered, consistent with a carcass that got actively torn apart rather than simply died and settled undisturbed. A biomechanical study modeling the bite force of a Basilosaurus isis skull put the force near the jaw joint at over 16,000 newtons, with roughly 8,900 newtons available at the canine teeth specifically, more than enough force to crush bone outright. And Dorudon itself has its own tangled taxonomic history with Basilosaurus worth including here, because it's genuinely reminiscent of the naming confusion we just walked through. For decades in the 19th and 20th centuries, researchers repeatedly floated and repeatedly argued over whether Dorudon fossils actually represented a distinct genus at all, or whether they were simply juvenile Basilosaurus specimens, not yet grown individuals of the same larger predator misfiled under a separate name. Robert Gibbs first proposed Dorudon as its own genus, then reversed himself, concluding his specimens were probably just young Zeuglodon after all, before Louis Agassiz at Harvard pushed back hard, arguing the teeth in question belonged to neither a juvenile animal nor to Zeuglodon specifically, but to something genuinely distinct, exactly as Gibbs had first thought before he talked himself out of it. Decades later, in 1936, paleontologist Remington Kellogg examined more material and again leaned toward a juvenile interpretation, before further, more complete adult Dorudon specimens finally settled the question for good. Dorudon is real. It's a genuinely separate genus, sitting in its own subfamily, Dorudontinae, distinct from Basilosaurus's own subfamily, Basilosaurinae, related but not nearly as closely as a century of back-and-forth confusion might suggest, which makes the predator-prey relationship between the two genera even stranger to sit with. Basilosaurus wasn't just eating a smaller version of itself. It spent a good chunk of scientific history being mistaken for one. One more honest complication before we get to the most current thread in this whole story. Basilosaurus had a notably small brain relative to its enormous body size. Without the room in its skull for the melon organ modern toothed whales rely on for echolocation, and that's regularly cited as evidence it wasn't operating with anything close to the behavioral or social sophistication of a modern dolphin or whale. That's a reasonable inference, though it is an inference, not something anyone can measure directly from an extinct animal's behavior. And it's worth adding a real nuance here, rather than leaving it flat. A 2021 study looking specifically at brain size evolution across early cetaceans found that relative brain size actually increased at the point basilosaurids like this one first split off from more primitive earlier whale ancestors, meaning Basilosaurus wasn't some kind of evolutionary dead end on the brain front. It represented a real step up from what came before it. It just still sat well below where later whale lineages would eventually land, with the bigger jumps in relative brain size showing up afterward, closer to the end of the Eocene and again much later in the Miocene. Now, the most recent thread, and it's a genuinely current one, still actively being argued over as of the last couple of years. In 2023, a team led by Giovanni Bianucci described a different, distantly related early whale from Peru, Perucetus colossus, built from a partial skeleton first uncovered over a decade earlier by paleontologist Mario Urbina. The headline claim out of that paper was enormous, based on extremely dense, heavily thickened bone structure, a condition called pachyostosis, similar to what keeps a modern manatee weighted down near the riverbed. The team proposed a body mass somewhere between 85 and 340 metric tons, with a central estimate around 180 tons, potentially rivaling or even exceeding the largest blue whales ever recorded, despite Perucetus being considerably shorter overall. It made headlines everywhere as a potential new record holder for heaviest animal in the history of life on Earth. It didn't hold up. In February of 2024, researchers Ryosuke Motani and Nicholas Pyenson published a direct rebuttal, arguing the original mass calculation assumed skeletal mass and total body mass scale together at a consistent rate as animals get larger, an assumption that doesn't actually match how real living animals scale, and that the original estimate overstated how much Pachyostosis alone can inflate total body weight. Using manatees, the very animal the comparison was based on, as a corrective example. Motani specifically pointed out that the original 180-ton estimate would make Perucetus so dense it would have struggled to physically reach the surface to breathe, a serious practical problem for an air-breathing marine mammal. Their revised estimate landed considerably lower, somewhere between 60 and 70 tons for a 17-meter individual, up to around 110 tons at the largest end, putting Perucetus in roughly the same weight class as a large modern sperm whale, nowhere near a blue whale's mass, which tops out somewhere around 270 tons. As of the most recent published analysis, the honest answer is that Perucetus almost certainly wasn't the heaviest animal that ever lived after all, and the title most likely still belongs to the blue whale, exactly where it stood before this whole story started. Perucetus and Basilosaurus are relatives in only the loosest sense, both members of the same broad early whale family, Basilosauridae, but not close cousins within it. Still, it's worth including here because it's a genuinely current example of exactly the same kind of correction that defined Basilosaurus's own story almost 2 centuries earlier, a dramatic initial claim. Walked back once other researchers actually checked the underlying math, playing out in near real time instead of over 150 years. So, an animal whose entire genus name is a fossilized mistake, king lizard, for something that was never a lizard at all, a name locked in place permanently by a rule of scientific naming that doesn't care how wrong the original guess turns out to be. A body built like nothing swimming in the ocean today. Hind legs too small to walk on, likely kept around for one very specific reason that has nothing to do with getting anywhere. Direct proof it hunted the calves of its own close relatives, after a full century of scientists being confused about whether those relatives were actually just its own children, and a family tree that, within the last 2 years, produced and then walked back a claim about being the heaviest animal that ever lived. The same basic pattern of an initial dramatic read, getting corrected under closer scrutiny, just compressed from 2 centuries down to about 6 months. Alright, that closes out this run of sea creatures, so it's time to head back onto dry land. And since we just spent an entire video on an animal named after the wrong idea of what it was, next time we're covering an animal saddled with almost the exact same problem from the other direction. Dimetrodon, an animal that shows up in dinosaur toy sets and dinosaur documentaries constantly, despite not being a dinosaur at all, not even particularly close to one, and what it actually was instead turns out to be far more relevant to your own family tree than to anything with feathers or scales. That one's next. Let me know in the comments what you want cataloged after that, and subscribe to Claw Catalog so you're here for it.